explain how we made a transfemoral implant design. So for a patient who suffered a high-level transfemoral amputation, um, he has two options to attach a prosthetic leg. One is by using a conventional socket, and the other one is by using an Osho integrated implant into the bone, the femur bone. So, due to medical recommendations, the transfemoral implant is better because the patient will get better sense of ground, since the prosthetic leg will be attached to the implant and this one to the bone, which sends the info into the brain. Also, a conventional socket prosthetic can cause skin sores, skin breakdowns, and infections due to rubbing. So we're going to design a transfemoral implant for a 170 pounds patient. So this implant should be able to support this patient daily activities. So first, what we did was to design the implant and the coupler that is going to attach the implant into the prosthetic leg using a CAD tool. In this case, it was SolidWorks. So this is pretty much the assembly and all the parts that are going to be um, transferred into ANSYS in order to perform an analysis to evaluate if the implant and the coupler are going to support the patient's weight. We started with an initial design. These are the dimensions, and we perform an analysis in the simulation tool, like I said before. So we transfer the CAD model into ANSYS. We apply the load that corresponds to the body weight into the system, and we got the following results. As we can see, we got a really high stress in the stem and in the coupler that are way higher than our limit, which is the yield strength. So what we did was to redesign, changing some diameters and increasing them in order to increase the strength of the components. So we did the analysis again, we solved, and we got the following results with the redesign. So what we have here is that now the stem higher, lower stress, and also the coupler. So these results are really good. In there we can see that we have 625 megapascals for the stem and 664 for the copper, which both are way lower than the yield strength that we talked before, that is about 780 and 90 megapascals. So in this analysis, since it was kind of complex, we did with a coarse mesh. We wanted to do it again with a finer mesh. So what we did was to apply the self-modeling technique, in which we choose our critical parts. We applied the loads, and we run the modeling simulation again. We also applied some fillets into the sharp edges in order to avoid higher stress at this point. And finally, we have our results. In this case, we can see that we have a really lower stress in the stem, and the project is ready, and we have these conclusions.